Hi, good morning. So today we're going to sort of do a lot of the same things that we did last time, that we did specifically for the case of framed Cobordism, but we're going to do it for unoriented Cobordism, and we're also going to spend a little bit of time talking about where mumble stuff Cobordism comes in. And we're not going to do anything specific with that, but I'm just going to be pointing out places in the proof where I'm saying, hey, look, this is where I'm using unoriented. You could change this right here. And then I'm going to point out why some of the, why it isn't that we only care about framed Cobordism. Okay, so last time we showed that the framed Cobordism ring is isomorphic to these stable homotopy groups of spheres, whereby showed, I didn't talk about the ring structure. I didn't even actually talk about the group structure. I just showed it was a bijection of sets. Nobody called me on that. I was very amused. I never actually talked about the group structure at all. So one of the things we're going to do today is talk about group structure. But one of the things that happened is that we really needed the framing in order to construct these maps. So we're going to go through the Pointryagin and Thom construction again today in more generality and talk about why you don't actually need those if you're not trying to land in spheres. But first, yesterday at the end, I mentioned a bunch of transversality stuff, and I didn't actually tell you what it was. So I'm going to start by telling you what transversality is, because it's actually going to come up. So definition. So if we have F, a smooth map of manifolds, sorry, I'm going to have to pause and think about how to use this board properly. And I is an inclusion of a submanifold, and the only reason that we need a name for this is that because we're going to need the derivative, the tangent space to M. So of a submanifold, then F is transverse to I, and I'll just write down the notation for this, even though I don't think I'm actually ever going to use it. So we have the following map. We have dF plus di, which is a map. Oh, sorry, I didn't tell you what points we're at. Eraser? So if for every point of x, and, for every point of m, and for every y in the preimage of x, that's how I'm going to use the board. The map, so we have df, and then we add di, and this is a map from the tangent space of y and the tangent space of m to the tangent space of x. And this map needs to be surjective. So you can sort of see what does it mean when it's zero dimensional, we want this to be the same as just something being a regular value. So when something is a regular value of a function, that means that the derivative is surjective. And you can see, okay, if M is a point, then this is a trivial space. And so this isn't, so all this says is that for everything in the preimage, dF is surjective. So you can see that this really is just a strict generalization of a regular value.
Is that TXM?
TXM. So now the idea is that it doesn't have to be surjective, but the only places where it can be non-surjective is sort of in the direction of M. So if M already covers a direction, that's fine, but otherwise F needs to hit everything. So that's what transversality means. But morally speaking, it means you're not tangent to things. Your preimage is going to have the right dimensions. like things are going to work out in the general position case rather than the crazy things are happening case. So this is sort of a differential version of things being in general position or things being a generic point or things, those kinds of things. These are not points where weird stuff is happening. These are points where reasonable stuff is happening. Yes. And you pretty much prove it with the inverse function theorem, implicit function theorem, like stuff. It's pretty much just calculus. I say it's pretty much just calculus. Actually, a really important result that it's surprising that people didn't see before Thom, which is a lot like the Thom isomorphism now that I come to think about it. But it's on its face, it's very, very simple. And then the key result of Thom is that this is not, these things are not rare. So the set of maps transverse to I is dense in the mapping space. Now, we're assuming these are smooth manifolds. If they're not smooth manifolds, then you have other stuff that needs to happen, like you need to remove the non-smooth points. But in general, if you're in nice situations, it's dense. And if you're in nice situations, the set of smooth maps is also dense. So this means not only the thing that we were talking about yesterday when we said it needs to be that we can just homotope it to something smooth and then homotope it to something transverse and it just works. This means that you can always make as small a perturbation as you like, and you can still get a map that's nice. So we actually don't need that because we don't care about the size of perturbation in this case. But in general, sometimes you do, and it's good to know that you don't need to worry. You can make as small a perturbation as you like. Yeah, so in fact, the way that these results are usually proved is you show that the transverse ones are dense in the smooth ones, and then you show the smooth ones are dense in the whole thing.
So the transverse ones are a subset.
Yeah. Yeah, smooth map. Yeah. Right, so, yes?
So it seems like if X is like R infinity and M is dimensional, or so
Well, so that, so then things just aren't going to be, but we should, yeah, yes, yeah, automatically. Right, so, yeah, sorry, that's a good point. If you need to have a point in the preimage. So if you're much smaller dimensionally, you just exclude the entire image, and then you're done. But it's kind of boring. Okay. And the key property that we need is that if F is transverse to I, then F inverse of M is a smooth manifold of the appropriate dimension. I didn't label dimensions, but I'll just put of the appropriate dimension. By which I mean it's the dimension of, well, whatever it is that you're expecting it to be. Write down the dimensions and I can't do arithmetic this early in the morning. Whatever the correct arithmetic expression for the dimension is, that's what it's going to be. Yeah, okay. So somehow this works correctly. So you can remember yesterday when we were trying to construct Cobordism classes from maps, we were taking the preimage of a point and saying, oh, it's going to be a manifold. Now we won't be able to take a preimage of a point. We're going to need to take a preimage of a manifold, so we need this. So this is the property we need. And the reason we care is that we want it to be the case that for any homotopy class, we can choose a representative that gives us this nice property. And what this stuff says is, yes, you can, and you don't even need to look at the entire homotopy class. You can even just look at things close to what you started out with. Okay. So this is the transversality stuff we're going to need. Now, I also want to spend a little bit of time talking about Thom spaces explicitly, because we've actually been using them all day yesterday, but we didn't really name them, and we didn't say what they were, and we didn't list any properties. So I'm just going to do that because we're going to be using them all through the lecture, and I want to make sure you've seen everything just written out. So definition. So we're given an n-dimensional vector bundle, E over B. And then the Thom space of E, and it's written, sometimes it's written Thom space of E like this, and sometimes it's written Thom space of E like this. And, you know, whichever one you like, I'll be using this one, but other people will use this one. It's the same thing. Is one of the following. So here are three different possible definitions. So one, so we're going to take a sphere bundle. And we're doing this by, so this is a sphere bundle that you get by 1 point compactifying every fiber. And that, you know, all of your fibers fit together nicely, so all these points at infinity will fit together nicely, so it actually gives you a bundle by 1 point compactifying the fibers. And then the Thom space of E is the quotient of E hat by the section at infinity. So you've added a new point above every point. That gives you a section at infinity. You quotient it down and collapse all of those to a point. That's the Thom space. Second definition, if B is compact, then the Thom space of E is the 1 point compactification of E. And 3, if you have a subdisk bundle, I didn't give it an, I'll call it D, then the Thom space of E is D quotiented out by the boundary of D. You can take any one of these definitions that you like if it applies. They're all equivalent when they apply. We only care about the homotopy type of the Thom space, so it doesn't matter exactly which one you take. But the important thing is that you do something consistent. Generally, when B is compact, people like this definition because it's the easiest one, and this is the one that Jesse was discussing yesterday. But a lot of the time, we don't have a compact base, so we don't want to only have this definition. And then these two definitions are really the same thing, but once again, sometimes it's easier to work with a subdisk bundle because you have one already in a nice, natural way. Sometimes you don't want to worry, do I have a subdisk bundle, how do I construct it? And then the definition 1 will always work. But, so I put definition 1 because it always works, but 2 and 3 are often easier to work with. So those are the ones that you often want to keep in mind if you can use them. And so an example that you saw yesterday, but maybe didn't realize that this was exactly what I was doing, is that when we have the trivial bundle over a point, then its Thom space is exactly SK. And we were using this yesterday when we did this process where we collapsed by a neighborhood and then we mapped it. We said, oh, we can use the framing to map it to a sphere. what we were actually doing was we were mapping to a Thom space. And you'll see this more explicitly in a second when I start talking about how to do it in the unoriented case. But wherever you have a sphere on the right-hand side of a map in yesterday's lecture, it's actually the Thom space of this trivial bundle over a point. So if you get confused today, but you understood yesterday and you want to go back and look over that, you should be keeping that in mind. And then what we're doing today is just a direct generalization of that. Okay, and exercise, which is quite important. So this is something that I drew yesterday. Suppose that you have a map of bundles. And this is a pullback square. So we get a map from the Thom space of E prime to the Thom space of E. And you saw this square yesterday, and this is what we were using. Last time I said, oh, this is a trivial thing. This is going to be our framing, a way of expressing it as the pullback of a trivial bundle. And then we get this map to a sphere. Well, this time, this is the more general form. Okay. So there's a bunch of really important examples of Thom spaces and Thom spectra. And they all start with M. I'm not really sure why they all start with M. Maybe Peter can tell me why do they all start with? Anyway, when you see something called M something something something, that means it, yes? Oh, I don't remember. Maybe. Okay, so if Thom used M, then that makes more sense. But anyway, so everything starts with an M. So if you see a spectrum or a space called like MOK or a spectrum called MO, that's obtained via Thom spaces. So definition, MON is the Thom space of the canonical vector bundle on BON. Not the canonical, whatever one it's called, the universal bundle. Thank you. Regardless, whichever one, the one that, to a Grassmannian assigns the plane that the point represents, that one, it's gamma n, and MON is T of that. MUN is T of the tautological bundle on Grassmannian of complex planes. And in general, if you have M something, 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 it's the Thom space of the tautological bundle associated to those kinds of vector bundles. So those are what M's mean. Okay. Okay. And so, but right now we're dealing with just vector bundles, so we're just going to be dealing with O. Oh, and one other thing. So yesterday, Jesse mentioned the Thom isomorphism, and I just wanted to rephrase it in terms of Thom spaces. The Thom isomorphism goes from, this is an N bundle, so it goes from HK of B to Hn plus K of the Thom space of E. This is exactly what Jesse said yesterday, only it's slightly more general because he was assuming that B is compact and it doesn't need to be. This is just works in general. Okay, any questions so far? Okay. So now we're just going to do the Pontryagin Thom construction again, but we're going to do it in more generality, and we're going to point out where we're using stuff. So again, the Pontryagin Thom construction. Oh. Yeah, okay, good point. Okay, yeah, so just as a point, so BON is the Grassmannian of n-planes in R infinity. And something I want to point out, it's not a manifold, it's infinite dimensional, which is going to be a bit of a problem for us when we want to use transversality. So this is, warning, warning, sharp curves ahead. We're going to need something to deal with this because what's going to happen is we're going to end up with a map into BON because we're going to have a bundle, an n bundle, and it's going to be the classifying map. And we're going to want to use transversality, and then we're going to say, oh, but we don't have manifolds. And the whole thing about transversality was that you had manifolds. And what are we going to do? So keep that in mind. But let's just keep going, and we'll be cautious when we get to the place where we need to be cautious. So we're given a manifold M, and we're going to choose an embedding. I'll say this is an n-dimensional manifold. So we're going to embed it into Rn plus k, which always exists for k big enough. So we don't need to worry about that. And then we have a tubular neighborhood. E, which again, recall from yesterday, is that we can think of as an embedding of the normal bundle. And then, again, we're going to look at E modulo the boundary of E. And so, again, we get that the Thom space of the normal bundle is isomorphic via exactly the same kind of thing we did yesterday. So I'm not actually going to write out the whole long sequence of isomorphism. This is Sn plus k modulo Sn plus k minus E. And so, but nu is a vector bundle, so we get a pullback diagram like this. We have this. And, well, from the exercise, this means that we get a map from the Thom space of nu into the Thom space of gamma k. And this is really the important part. We're now pretty much done. All the rest of it is just pre-composing and post-composing with reasonably easy stuff, because we have maps. So we have BOK to BOK plus 1, and so on and so forth. And then we have a thing which is BO, where you can think of O as infinite matrices, where eventually they are the identity. And we get maps between them, and we get maps between the vector with the tautological vector bundles between them, and so we get a map of Thom spaces. So we have maps Thom space of gamma k to the Thom space of gamma k plus 1, and so on and so forth to the Thom space of, I'll just call it gamma to be the same type of thing, even though it's no longer a Thom space, it's a something. I'll just put it in quotation marks. There isn't really a something at the end, because you don't have a proper vector bundle there. And so we're just going to take the co-limit of those. Yeah, you do. Because really you do this as a spectrum. But anyway, you're right. Yeah. Yes. Yeah. Right. So that's an exercise on your problem set today, checking that if you take a bundle and you add a trivial bundle to it, then when you get is an n-fold suspension on the Thom spaces. And that's not very hard. It's on the problem set, right? It's on the problem set, right? Okay. But yeah, no, anyway, it should be on the problem set. I'm assuming it's on the problem set. So yeah. So, right, so what we end up with is, we're going to define pi n of MO to be the colimit over k of pi n plus k of t of gamma k. And the colimits here go the same way as they did for the stable homotopy groups of spheres, where for each one you have a map from Sn plus k to T gamma k, and then you suspend it and you compose it with this map, and that gives you the map to the next group. And you just keep going. And so what we end up with, using the fact that we have these, is you can, so here we have a map, so we get a map Sn plus k to T to the Thom space of nu, just because this is a collapse, so you could collapse it. And then we go to T of gamma k, and this is an element of pi n plus k of T of gamma k, and we have a map from here to pi n of MO.
Just like the vertical extension theorem, the independent of K is large relative to K through that.
Yeah, so Thom wasn't doing it this way. He was saying, oh, eventually, for big enough k, I think you need k to be like 2n or something like that. Anyway, if you take k to be 100n, you're definitely fine. So there's some lowest bound, but I don't remember exactly what it is. It should be in Thom's paper, but it doesn't really matter. Just take k big enough, and you can just, these will be the same. So you don't, this map will just be like the identity, sort of, and a proper isomorphism. So that's what you can do there. So what the Pontryagin and Thom construction has done, so as a summary, we have that M maps to an element which I'm going to call PT of M, which is in pi n of MO. And PT obviously stands for Pontryagin and Thom. So we have this. Now, a couple of notes about stuff Cobordism. Where did we actually need that were unoriented? Where were we actually using anything? Well, I said I have an embedding, and then a tubular neighborhood, and then that the normal bundle is just a K bundle, and so has this map. Everything else that I did was just following everything else through and pushing it through. So if you have Cobordism with structure that you care about, this is where you modify it. You say, okay, I have an embedding with the structure that I care about, and then I have a tubular neighborhood that is related to the structure that I care about, and then that produces a classifying diagram like this into something else. And this something else, if you have complex structures, it'll be to BU. And if you have spin structures, it'll be to B spin. And if you have mumble stuff structures that you could make, and you have a classifying space for them, you'll have a diagram into that. And then all of the formal stuff goes through. You might need to figure out what colimits mean. You might not have a Freudenthal suspension theorem for whatever stuff it is that you care about. But this colimit part will always work. You will always end up with a map like this after you take the colimit. And so if you have any other flavor of Cobordism that you care about, this is how you generalize this.
We were emphasizing the stuff always means structure on the thing.
And you can see that right here, because where we actually needed, like how we actually constructed, hey, the thing followed me. the way that we actually constructed this is by using the structure on the normal bundle. We never actually used anything with a tangent bundle. So that's what's going on there. So, I mean, we're going to be checking this as an isomorphism and actually say like a group homomorphism, unlike what we did last time. But I want to make a couple of comments about why we care. Yesterday, I sort of said, oh, frame cobordism, it goes into stable homotopy groups of spheres. And so we can learn about stable homotopy groups of spheres by looking at things we know about Cobordism. So like manifolds give us elements in the stable homotopy groups of spheres. There's a bunch of manifolds we understand reasonably well. We can study the elements that those give us, maybe learn something about stable homotopy groups of spheres, and that was actually how this was used. But this MO looks really mysterious. I mean, you took something that we kind of understood, and then we made it really big, and then we took the co-limit, and then we end up with something completely crazy, and why is that any better? You know, now we have stuff we kind of understand, which is manifolds, and then we're trying to use it to maybe understand something that, you know, we really haven't seen outside this context, so why should we care? But the thing is that, in fact, just like with cohomology, you know, you have homology, and you kind of understand it geometrically, and then you dualize it, and suddenly it becomes much harder to understand. But in a certain sense, it's easier because it has more structure. It has a ring structure. You can do a lot more stuff with it. And so by making it more complicated, you've actually made it easier to work with. Similarly, we actually know what these are. Jolie is going to talk about that in the next talk, so I don't want to step on his toes. But we actually know what these groups are. We actually know what the groups MU are. And so what we can do is we can actually use the homotopy theory to learn something about manifolds. And somehow it seems a little bit crazy that by making this weird, crazy, several-stage, infinite-dimensional construction, we can end up with something much simpler, but we can. And that's sort of what's going on here. So this stuff, that information is really traveling in the opposite direction to the stuff I was talking about yesterday. Because yesterday, we don't know enough about homotopy groups of spheres to really pull back a lot of information. But here, we know a lot. And we can really say a lot about what's going on there. And any manifold can be made unoriented by forgetting orientation. So unlike with framed manifolds last time, where we might not have a framing, and so some manifolds might not even appear, all manifolds have a role here. So that's right. So that was what I wanted to say about that. So this is important, and the information is flowing in the opposite direction. Okay. And just like last time, we might. Question? Is there a question? No. Okay. Just like last time, we need to worry about how well defined this is, because we made a whole bunch of random choices here. We are meant to start with a Cobordism class, and instead I just started with a given manifold. I chose an embedding, which I could have chosen a different one, or I could have chosen a different dimension, or both. And once those are chosen, you're kind of fine, but that's a lot of choices. That's like 3 choices right there. You really do need to check that those give you the same class. I'm going to give very, very rapid, not even really proofs, but like summaries of ways that maybe you could construct a proof. A, because we saw a lot of this last time, and B, because I don't find it terribly interesting, but I want you at least to remember that it exists. Yeah, so this is also why I'm not going to spend much time on it, but I don't like leaving the possibility that things are badly defined, so I'm just going to list the properties you need to check and give slight hints about how to do it, and then go on to transversality. So point 1, making K larger does not affect the answer. And the reason for this is that if you just increase k, so you have an embedding of m into Rn plus k, and it's like Rn plus 4, but you messed up and you wrote down Rn plus 500 million instead, even though it doesn't touch the last bunch of coordinates. And that's fine because, so nu changes to nu plus r to the something, which means that we get the map that we get the Thom space of nu to the Thom space of gamma k goes to the lth suspension of the Thom space of nu to the lth suspension of the Thom space of gamma k, which will then map to Thom space of gamma k plus L, and by the same way as in the colimit, and in the colimit it all works out. So that's just not changing the embedding, just going into a bigger dimension. So 2, changing the embedding. Doesn't affect answer. And the reason for this, and this is the only sort of important conceptual step of this, is so if we have 2 different embeddings, then there exists the following square where these 2 are also embeddings that commutes. And so all you really need to check is that if you compose a iota with another embedding, then it doesn't change the answer, and now you have a way of relating these 2, and you do that in a similar way to the way you do this, and then the same argument and the colimit, it doesn't change the answer. And the last thing is if m and m prime are cobordant, they give the same answer. And this is the same as last time. Pretty much. You need to be a little bit more careful because this is one of the things I sort of skimmed over last time, but the cobordisms last time had a framing that made it easier to get framings on the endpoints. Now you don't have it. You just have the cobordism, and so you need to be a little bit more careful about how you do the Pontryagin and Thom construction, but you follow the same outline as last time, and it gives you what you want. So I'm not, and you explicitly from a cobordism get a homotopy, and so I'm not going to worry about exactly how that works. I'm just going to tell you that it works, and then not worry about the rest. Okay, so the question is, how do we construct an inverse and then check that it's an inverse and that things work, and where does transversality come into all of this? No, wait, one more thing. Again, I almost forgot the group structure, and nobody has called me on it. I've constructed a map, but I haven't told you why it's a group structure, why you get a group, why it's a group homomorphism. So let's see, remember last time I said oriented cobordism groups are labeled with this big fancy N for some reason. So anyway, so we have this unoriented cobordism, and we're constructing a map into pi n of MO. And at the moment, we just have this as a map of sets. So now the question is, what happens? Well, the thing to note is that checking that the identity goes to the identity isn't very hard, because you have the empty set, and you can pick a neighborhood, and you just look at it, and you end up with a constant map. So you're good. Like the empty set actually just gives you the constant map. You don't need writing down the null homotopy is easy. Everything is good. Right, but it's a place to start. If you're trying to show something as a homomorphism of groups, a place to start is checking that the identity goes to the identity. And it's a good place to start because often if something is going to go wrong, it's going to go wrong there. And so it's actually, and it's an easier thing to check than group operations. Like you have the identity, and if something is going wrong there, then you're just, clearly something is really off and you need to start rethinking things. Okay, so what about the group operation? Well, over here it's disjoint union, so, and they go to the disjoint union, and over here, it's, if you have a map Sn plus k into the Thom space of gamma k, so if you have two of these, f and f prime, then what you do is you take Sn plus k and you pinch it. You take the diameter, you take the equator and you collapse it to a point, and it gives you two spheres. So this is called the pinch map. So you get Sn plus k wedge Sn plus k, and then you do f wedge f prime. So you do the first one on the first one, second one on the second one. So we want to check that the Pontryagin-Thom construction takes the disjoint union to this kind of thing. So how do we do this? Well, we start by choosing an embedding. And luckily it says choose, and we have already proved that it doesn't matter what choices you make, so I can make whatever choices you like. So I'm going to take an embedding of the disjoint union of M and M prime in a way that maps M into the left half plane or half space and M prime into the right half space. So here I have M. Here I have M prime. This is an embedding of M. This is an embedding of M prime. This is an embedding of both together. Here are my tubular neighborhoods. And now the important thing is how we do the collapse. There's two ways of doing the collapse. Remember, if you're collapsing a bunch of stuff, you can collapse a sub-bunch of stuff and then the whole thing, and it doesn't actually change anything. So first off, we can think of all of Rn plus k as a copy of Sn plus k. So you do Sn plus k, and then you collapse. And you get the whole thing, and you get the Pontryagin-Thom construction of M disjoint union M prime. On the other hand, I can do the collapse in two stages. I can first collapse this line. So I sort of get two half spaces lying on either side. And then I can collapse everything else. And so this gives you a map. So this two-stage collapse gives you a map first from Sn plus k to Sn plus k wedge Sn plus k. And then you do the collapse on either side. And this gives you the pinch map. And then you get the sum of the two Pontryagin-Thom construction maps. So this gives you the Pontryagin-Thom construction of M plus the Pontryagin-Thom construction of M prime. So these are the same, because as I said, if you're collapsing, you can collapse a smaller thing and then the whole thing, or just all at once. And so these two are the same, and that's the proof that it's actually a group homomorphism. Notice I didn't use anything at all about the particular case that we're in. This proof works for every kind of cobordism you care about. So you only really need to do it once. Okay. So, right, so we have that. So what's the inverse? Well, okay. Any questions about this so far while I'm erasing? Okay, So how are we constructing this inverse? Suppose that I have an element alpha in pi n of MO. And we want to construct a manifold from it. And so how are we going to do this? Well, first off, pi n of MO is defined as this colimit right here. And as Peter said, we have a Freudenthal suspension theorem, although it doesn't matter for what I'm about to say. It's just going to be an element in one of these for some k. So choose k. And we know that alpha actually lives in pi n plus k of the Thom space of gamma k. So in particular, it's given by a map Sn plus k into the Thom space of gamma k. And this has a map from, actually, I'm going to draw the other map. This has a map from BOK. This is the 0 section. And if we were doing this last time we didn't have this Thom space of gamma k. Last time we had a sphere here. And we just had a point. I said, oh, look, 0 lives in here because this sphere is really RK. It has a 0. 0 lives in there. And we're just going to take the preimage of 0. And we need to make sure that 0 is a regular value of this. And we homotope it so that it is mumble, mumble, mumble Sard's theorem. And then we get a manifold. Uh-huh. Stop! Let me give my talk. I already warned them this was going to happen. Oh, okay. There was a warning ahead of time. Anyway. Damn it! Now I have no punchline. I'm going to need to think of something else. Okay. So we have the 0 section living in here. And what we'd really like to do is just say, let's take the preimage of the 0 section. And and we can just get a manifold here. And mumble, 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 transversality, mumble, 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 it works. Unfortunately, it doesn't work because, as Peter just pointed out, it's not a manifold, it's infinite dimensional, and transversality, which used to be up there even though I erased it, requires you to have manifolds. So what do we do? Oh no. We said, okay, BOK is the Grassmannian of k-planes in R infinity. And the problem is that infinity up there. If you're just looking at k-planes, you're fine. But it's the R infinity that's the problem. But as almost always in topology, compactness comes to the rescue. This is compact. Yes, exactly. Go spheres. So in fact, what is this? This is the union over all M of the Grassmannians of k-planes in Rm. Because every k-plane in R infinity can only hit finitely many coordinates. And so this is an infinite union, and this is compact, so it's going to hit some finite one of these. The image of this map, so we have this map F. So F is actually a map from Sn plus k into the Grassmannian of k-planes of Rm for some m. And now, each of these is a manifold. So we can use transversality. We actually have a Grassmannian of k-planes in Rm here that sits inside here. And in fact, there's a tautological line bundle gamma mk here. And in fact, you will get something like this, and F will factor. So I will draw F back in. But F will factor through that. And now, okay, I want to say now we have all manifolds and we can use transversality, but that would be a total lie. Because Thom spaces aren't manifolds, because they have this point that you added where you collapsed a bunch of stuff, and sometimes, like last time we had a sphere, that's a manifold, yay spheres, but most of the time they're not manifolds. There's like all this stuff next to this one point and it doesn't look like anything and it's bad. But that's fine. I love saying that's fine, it's okay. Because this is the zero section, again. And the zero section isn't anywhere near that point. That point is the point at infinity. Remember, one of the definitions was you one-point compactify every fiber, and then you collapse all of those infinite points to a single point. So those are that bad point is the infinite point. And so it's very far away from here. And transversality, you had denseness. I said, you can perturb a map as little as you like and make it transverse to this. And in fact, all that matters is what's going on near the manifold you care about. And this manifold can't see that bad point at all. So mumble, mumble, mumble transversality, mumble, 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 things work. And so I'll call this F tilde. And so you take F tilde inverse of the Grassmannian of K-planes of Rm. And you get this, and this is the manifold we want. And you can see how, if you remember what we did last time, you can see how this is very similar to what we did last time. It's just a sort of a higher dimensional generalization. Because before we were looking at points and we had a sphere and everything was good, and now we need something more complicated. But it's more complicated in exactly the way that the transversality theorem was more complicated, because we want it to be transverse to a submanifold rather than regular at a point. This is exactly the same thing. And so that's what you get. And then the proof that this is a bijection, we no longer need to worry about the group structure because we did actually prove the group structure. Goes very similarly to the way it went yesterday, although I did kind of gloss over it yesterday. But you can go look it up. It's in a whole bunch of various places. I only have a few minutes left, although I did start late, so I have more minutes than I thought I did. Let me see if there's anything specific I wanted to make sure to say. No, okay, right. So this is, there's a bunch, you need to check this as, yes? Mm-hmm. Mm-hmm. Yeah. Mm-hmm.
In addition to saying that, are you saying that the
Mm-hmm. Yeah. Yeah, because I sort of implicitly used that without saying it. But yes, that is exactly what happens. And you can see it because, okay, you have a vector bundle and you have a plane above a point. Okay, and the point is sitting inside some Rm, so that plane is going to be sitting inside that Rm, so that's fine. And then for every point and fiber over that point, it's going to be inside some Rm. So yeah, the exact same thing works for the Thom spaces. And you can just check that. It just follows because the gammas are the colimit, and then it's just like writing it down.
As soon as there, we turned the colimit into the disjoint.
Oh, yeah, but we don't have disjoint unions. We just have. That's not a smash. That's a wedge. That is a colimit. Here, yes. But we're not taking disjoint unions. We're just taking unions, and for this kind of thing, it works. I agree that it doesn't work in general, but for this kind of thing, it works. Yes, F is a representative for alpha. Alpha is a homotopy class. Thank you. I'll write that down just so that alpha is the homotopy class of F. But yeah, I can't just put alpha because it's not a map. Okay, other questions? So I've been saying you can do this with mumble, mumble, mumble stuff Cobordism, and this is where you change it, and this is where this works. But there's two kinds of ways of changing what kind of Cobordism you have, and I wanted to quickly comment about what those are. So we have, so before we've generally just been, oh, we have manifolds, and we know what manifolds are. And we might want to put some extra structure on them, like a framing or a complex structure or an orientation. But the manifold itself doesn't change. But what if you want the manifold itself to change? What if you want a piecewise linear manifold? Then transversality, which really relied on the smoothness of the underlying manifold, no longer works. And so you no longer have, you can no longer use any of these techniques, it looks like, because transversality fails, and as soon as transversality fails, we can't do anything like this. But in fact, you can. So the way you can do these same kinds of things with the cobordism with other kinds of manifolds, like piecewise linear manifolds, but you need generalizations of transversality as well. And somehow, when we've been discussing this, it hasn't really looked like the most important thing is transversality, because I've been talking about Thom spaces and about all this other stuff. But somehow, once you have the definition of a Thom space, everything else is sort of formal. That's one of the brilliant things about this definition. Somehow, all of these cool things just fall out of the definition, and you don't really need to work to get it done. But transversality is somehow the core. You can't construct this inverse at all without transversality. And so you need this fact that you can construct transverse maps. And you need a notion of what transversality means. And if you don't have a smooth structure, that all disappears out into the ether. And so one of the things that people have done with, say, piecewise linear cobordism is generalize the theory of transversality and then use that in order to construct this kind of theory. And it has turned out, in general, that the transversality is the hard part. If you have an analog of transversality, then you can do this whole theory, and it all works together. You might need to figure out what to put here, but that's somehow, in a very concrete sense, easier than generalizing transversality. So somehow, even though there's this theorem that I seem to really only be using once, it's the core of everything that's going on. So it's a lot more important than it looks at first. Okay, and I actually have more time than I thought because I started a little bit late. So I'm going to make a comment about proving that this is an inverse. So we haven't actually even checked that it's well-defined, really. We need to check if we have a homotopy, it turns into a cobordism. But that's just going to work the way it worked yesterday, because you're going to end up with an extra coordinate here, and then you pull back, and you end up with sort of an extra coordinate, and mumble, 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 it all works. The case of it that actually is sort of the hard case. Once you figure this case out, you can figure out everything else. Is showing that, well, it's showing the following. This is this map, that the Pointryagin-Thom construction is injective. So in order to show that, you need to show that if you produce a null homotopic map, then you were actually a boundary to begin with. And the way you do that is you do this, and you apply this, and you use it to construct an actual manifold using the null homotopy to produce this thing. So I'm actually going to tell you a little bit more about that, because it's actually important, and I have a couple of minutes. So how are we doing this? It was on this board. So obviously I just erased it. Right. So that was one of the things I was going to say. But anyway, it doesn't matter. What I was going to say is when you have, so we chose this embedding into Rn plus k, and this was sort of the first thing that happened. And that's, the thing is, you're good. You've already chosen it, and it turns out it sort of runs with you for the whole thing, and you end up with the same thing when you get back. But if you look at what's going on here, what we really need to check is that sort of, that this diagram already commutes, and we've used that already. So what did we do? We had this, we had Sn plus k, and we had it collapse to the top space of nu, and then we mapped it to the top space of gamma k. And we had this, but the thing is, we had it mapped to the top space of gamma k, but we didn't need to. We could have had it mapped to the top space of gamma n plus k, comma k, because we know where nu is. We've already chosen the embedding. We know where the vector bundle lives. We don't need to worry, what dimension does it live in? Can I find the appropriate dimension? It's there already. It's sitting there. We have an embedding. So we just do this, and then again we have, so here we have the Grassmannian of k-planes in Rn plus k, and then you just end up with m back, because that's what you do. That's what it is. That's how it's defined. M is the zero section of the normal bundle. That's how we defined it. So it's not, so the checking that you get M back is not actually a problem. Once you've checked that both maps together are well defined, you're good. But the hard part is checking that if you have a null homotopy that explicitly constructs a manifold with the correct boundary for you. And I'm actually going to leave that for you because it's actually a fun thing to try and do and figure out. But you actually, this is a way to, if you know that a manifold is a boundary of something, this is a way to explicitly construct the manifold that it is a boundary of, which I think is kind of cool. You pick the homotopy and that gives you the manifold. So anyway, that was what I wanted to say today.
Jolie, you need Ina to say something about the ring structure, or you kind of do it.
Okay.